All right, so the Claisen condensation is really similar to the pod that we just saw. Really all it is a nucleophilic acyl substitution where you've got an ester reacting with an enol or an enolate. So let's take a look at the overall reaction and then we'll go through the mechanism for this simple example. So we'll use ethyl acetate and then we'll use sodium methoxide followed by an acid workup. And I'm not going to show you the product right away. Let's just do the mechanism and try to figure out what the product might look like. So we've got these alpha protons off of the right-hand side, and we're going to treat this first with sodium methoxide, which we know is a strong base. A lot of people will stop and say, well, won't the ethoxide come in, attack the carbonyl, and then put the negative charge on the oxygen? Yeah, that will happen, but when it clamps down, it gives you the exact same product. So that's one important thing in this reaction is the base that you use, this ethoxide, needs to match the leaving group on this side. Otherwise, you might get mixed products out of this reaction. So let's make a little note of that. Use base that is the alkoxide. Whoops. Of your ester. All right, so now that we have that all set up, we know we can deprotonate these alpha protons. We'll clamp down. Now we've got our enolate, where we've got the negative charge on this carbon. Those alpha protons aren't that acidic, so we'll have a fair amount of neutral ethyl acetate around. And in this case, we know that this portion will be our nucleophile. This will be our electrophile. And all our nucleophile is going to do is add into this carbonyl, kick up electrons. Oops. Yeah, I did that right. And we've got an oxygen with the negative charge there. All right, what do you think the next step's going to be? Yeah, clamp down, kick off our ethoxide. And there we go. So when we look at these compounds that we form, these are called beta keto esters. The reason we call this a beta keto ester is the ester is a higher priority, and then we look over here and we say, all right, this is the alpha position, this is beta. We've got a carbonyl coming off that beta position, specifically a ketone, so we refer to it as a keto substituted ester, specifically a beta keto substituted ester.
So it has to attack a non-deprotonated one? Or could it also attack one that's been deprotonated as well?
In this case, it'll attack the non-deprotonated one. So remember that this first step that I've shown, I should technically draw this as an equilibrium, right? And so some of your enolate will be present in equilibrium, and as soon as you form your enolate, it will attack any of that neutral ethyl acetate, treating it as an electrophile. So let's go back up and fill in the box here. And we've got our final product. Does that make sense? pretty straightforward. It's kind of the crossover between this chapter and last chapter. Let's take a look at a variant of this called the cross Claisen. And we're going to use this guy, and we're going to use this, and then we're going to treat this with sodium methoxide followed by H3O plus. What do you think the product might look like for this? Yep. That's a good question. In this case, do we have multiple sets of alpha protons to deprotonate? Yeah, so in this case, we only have one molecule that has alpha protons, which plays in our favor, right? So we don't run into that mixed aldol problem that we saw on Thursday. So let's take a look at this. If we think about this carbon in red, that's going to be our nucleophilic enol, or our enolate, because it's the only position where we have alpha carbons. And we know it will attack the ester that we have shown, so methyl benzoate. It will pop off that methyl or methoxy group, and we'll get our crossed Claisen product. So really the only difference between a regular Claisen reaction and a cross Claisen reaction is that these two have to be different. So typically in a cross Claisen reaction, you have at least one ester and then one other carbonyl. So you can use two esters if you want, or only one ester and a different sort of carbonyl. You do have to watch out for mixed products though. So let's make a couple notes. Yep.
This example, why don't you get the two simpler guys to combine together? Like, why don't you get a mixture of products? I can see that there's no alpha protons, but why doesn't that?
That's a good question. So typically what you'll do is drip that methyl ester on the right into LDA to exclusively form the enolate of that right-hand side, and then you'll add it in. So that's kind of our segue for watching out for mixed products. Because you're right, if you just threw all of these together into a sodium methoxide mixture, you might get a couple different products out of this. So for mixed products, one solution is to use only one type of ester. To avoid a mixture. The other one we talked about yesterday was to use that LDA method, right? So, whoop. Strip the ester that you want to act as a nucleophile. Oh, thank you. Drip the ester that you want to act as the nucleophile. Into LDA. And then transfer to your electrophilic reagent. And on Thursday, last Thursday, I said the order of addition is really important, right? So in this case, I'm saying we're dripping our nucleophilic ester into LDA. Why don't I drip the LDA into our nucleophilic ester?
excess ester around, it will start reacting.
Exactly. If you're dripping in your LDA into your ester rather than the opposite, you'll only form a small amount of enolate that will attack any unreacted ester, and you'll get just a normal Claisen reaction to occur. So this is a useful way around that problem. Is by dripping it into a sea of LDA, you're exclusively forming enolate that never has time to find unreacted ester around.
So if you were writing that down as a reaction, would you like write LDA as your starting product, and then number one would be your ester?
Yeah, you can do it that way. Oftentimes people just show step one as LDA, and they will make it as a note in their procedure what's added to what. All right, the last one is use reagents where only one of the carbonyl compounds has alpha protons. So this is really similar to the aldol problem that we saw before, where we want to try to avoid mixed products, and we can do that by really carefully controlling order of addition or the reagents that we use. All right, so now I've got a challenge problem for you guys. I want you guys to try to work through the mechanism for this one. So we've got this diester. Does anybody know what this diester is called? I'll give you a hint. We've got, oh my, such good apple. So this would be diethyl I believe that's how it's spelled. Adipate. So diethyl adipate. We're going to treat this with sodium methoxide, and I want you guys to help me figure out what the product would be that we would get out from this. So I'll give you guys a minute to work on this mechanism. You guys can talk to one another too. You don't have to work silently. I'll give you guys a hint too. A lot of people are tempted to draw this linking up, so taking two of these units and linking them together, kind of like we saw in the previous examples. Why might that not happen? Yeah, so maybe some intermolecular forces. Also, entropy favors one molecule or 1 mole turning into 1 mole rather than 2 moles turning into 1 mole. So in this case, we might have it attack itself. How many of you guys want a couple more minutes to work on this? All right, I'll give you guys a couple more minutes and then we'll go through the mechanism as a class. But remember, you always go through that reading program. So yeah, it'll take it's not like that. All right, raise your hand if you still need a little bit more time. All right, I'll give you guys another little bit. All right, you guys, let's take a look at this one. This looks a lot harder than it actually is. The first thing we got to do is identify our alpha protons. We've got alpha protons right here and right here. Does it matter which one we pick? No, it's symmetric, right? You can pick any one of these alpha protons. So we've got our base. This base will come grab one of these alpha protons. We'll get our enolate out. Where we've got our negative charge right there. Now this negative charge could theoretically go after and attack another equivalent of diethyl adipate. However, entropy says that's not as favorable as it attacking itself. So in this case, we can have it attack in. Is it okay to go like that? No. You have to go through the tetrahedral intermediate. That's technically the correct mechanism. A lot of people get really stuck on these and they get quite flustered. The easiest thing to do is number, right? So 1, 2, 3, 4, 5. We've got a 5-membered ring of all carbons. So let's go through and make our 5-membered ring. 1, 2, 3, 4, 5. At carbon 1, we have this ester dangling off. On carbon 5, we've got oxygen with a negative charge. And we've got an ethoxy group. What's the next step? Yeah, clamp down and kick off our ethoxide. So we're almost there. However, we're going to run into a slight hiccup. Actually, let me clean this up a little bit more. So we've got ethoxide floating around. The reaction won't stop here. Does anybody know why? Yeah, our alpha proton right here is unusually acidic, right? It's smack dab in the middle of two carbonyl groups. So this excess, or this ethoxide that popped off, will go deprotonate that alpha proton, which has a pKa of roughly around 10 or 9, I believe. So what do you think a chemist would do if they wanted to isolate the product that's neutral rather than this negatively charged enolate? Yeah, just throw in water or acid. It's not that hard. So in this case, we just add some sort of proton source. And typically, whenever you see a Claisen condensation, you'll see some sort of proton source as step 2. The whole reason being that you really want to make sure that what you're isolating is neutral and not an enolate. And there you go. This is called the Dieckmann cyclization. I don't really care that you remember the name. However, it is important to remember that this is just a Claisen condensation that's within one molecule, so it's intramolecular. So there we go. Pretty straightforward reaction. However, you really only see the Dieckmann cyclization when you're forming 5 or 6 membered rings. It's not going to form a 4-membered ring because that's just too much ring strain for it. And same thing with 7-membered rings. It's not as likely that this will occur with a 7-membered ring. Yep.
So the second step we did is just to neutralize it?
Yeah, exactly. It's kind of like with a lot of the reactions we've seen. You have to do a final workup step. All right, so let's do a little synthesis practice. Let's take a look at this compound, and I'll ask you guys to help me propose its synthesis. Got a benzene ring, got a carbonyl, got a cyclohexane, and there we go. Question is, how will we make this? Looks like a lot of functionality. Remember, too, that this is our beta keto ester. What's up? To be what? It's a cyclohexane, yeah. Raise your hand if you're really stuck with this one, like this doesn't make any sense. Why did you draw this? Most of you guys are getting this? There's no shame in admitting you don't understand this. When I first saw these, I got super confused, and I was like, I don't understand how he's doing this, but I'm just going to do the mechanism, and I'm going to try to figure it out. But I'll show you guys the easy trick we did with our aldol reaction, and that is to identify your alpha and beta carbons, right? So we said that this is a beta keto ester. We know that the keto is coming off that beta position, so we'll label this position beta. We know that this is alpha because it's one carbon away from that ester. All we're going to do is retrosynthetically take our scissors and cleave the alpha-beta position. Just like we saw in the aldol reaction, we're always forming new alpha-beta linkages in these reactions. Okay, so now that we work backwards, we know that we have to have some sort of leaving group on here. So I'll just write LG. So this will be this whole portion of the molecule, right? And then the other portion that we have is just going to be the remnants. Oops, sorry, this should be cyclohexane. And there we go. So really all we're going to do is we're going to deprotonate these alpha protons, they're the only ones available, turn that into a nucleophile, and then do nucleophilic acyl substitution with the other half. So let's try to get a full picture of what's going on here. And we'll do the full forward reaction. What leaving group do you guys think we should use for this second component? I would probably use an ethoxy group, so make this an ethyl ester. The reason being that makes cleanup a lot easier, right? What base should we use in this reaction? Sodium ethoxide. We want our leaving groups to match the base. We'll use sodium ethoxide. And then in step 2, we said we oftentimes need to do this with an acid workup. So I'll just write H3O plus. And that will give us our final product. It looks way harder than it actually is. The key to synthesis planning this chapter is just identify your alpha and beta carbons and cleave those and work backwards. Does that make sense? Okay. Yep.
I have a question about the reaction before this one. Why don't you end up with an aldol? So when you got the lone electron pair there in the carbon, why doesn't it resonate up to one of the oxygens and then form the alcohol?
So let me get this right. Your question was, why doesn't this kick up electrons here and then form the alcohol, so your enol? So in this case, you would get an enol, but once you treat it with a weak source of acid, it prefers the dicarbonyl species. But you're right. Once you form this, the resonance structure could be have partial double bond character along that carbon-carbon bond. Does that make sense? Okay. All right, so let's do another mechanistic problem. Let's do sodium methoxide followed by an acid workup. And let's try to predict what our product would look like here. I gave you a hint too. This looks pretty similar to a mechanism we already did. Raise your hand if you need a couple more minutes for this one. All right. I'm actually going to remove the 1 and 2 and we'll go through the full mechanism just for practice. All right, what's the first step? Yeah, deprotonate alpha carbon. It doesn't really matter which one because it's symmetric. They're going to have similar pKa's. We get our enolate. Oops. Now what? Will this attack another equivalent of starting material?
I have an assumption.
Yep.
So, if it wasn't symmetric, would it favor either of the products over the other, or?
Yeah, that's a good question. If one of the alpha positions is more acidic than the other, that will exclusively form the enolate carbon and will attack the other side. However, you don't typically see that often. It's hard to control and predict. So it really just comes down to acidity. In this case, both alpha carbons have the exact same pKa due to symmetry. All right, so the big question is, will this attack another group or will it attack itself? That comes down to ring size, right? It has to be a 5 or a 6-membered ring. So let's number it. We've got 1, 2, 3, 4, 5. Looks like it works out. So if we go through and we number this, we've got 2, 1, 3, 4, and 5. We know off the 4 position we've got this ethyl ester group. Off of the 1 position, oops, sorry, I've goofed this up. Off of the 5 position, we've got oxygen with a negative charge and then an ethyl group. There we go. Then off of the 1 position, we've got this ethyl ester. All right, now that we've got everything labeled, we can clamp down, kick off our leaving group. We've got our carbonyl. Then last but not least, we know that this ethoxide is going to be floating around. It's going to favor deprotonation of this very acidic alpha proton. And then last but not least, we'll treat this with some weak source of acid in order to get our final product. One misconception a lot of people have with the Claisen condensation reaction is they say it's a condensation, why aren't we losing water? Well, remember I said on Thursday that a condensation reaction can be loss of any small leaving group. So in this case, we're kicking off ethoxide. So it's still considered a condensation reaction. That's one misconception. The other misconception is it always has to be between two esters. Not always the case, right? The main takeaway from this reaction is that an enolate plus an ester equals a Claisen condensation. This enolate that you're using in this reaction could be the enolate of an ester. It could be an enolate of a ketone. It doesn't really matter. Oftentimes textbooks will tend to use only esters in these, so two esters. However, you can use a variety of different reagents. All of them are classified as Claisen condensation reactions. All right, I think that's where we're going to leave off today. When we come back on Thursday, we'll get into alkylation of the alpha position. And then I would encourage you guys to try to do the extra credit pod that's due Thursday.
So, just to kind of like reaffirm the question I just